Hello, my name is Paulo Coelho, and I will present GeoPaxos Plus, Practical Geographic State Machine Replication. This is how the presentation will follow. I'll start by presenting the questions we try to answer, followed by the system model and some background related to our work, followed by GeoPaxos Plus, our protocol, and then some results about our experimental evaluation, and we conclude with some final remarks. Online services are more and more present in our lives, and they typically have clients spread all over the globe. And this imposes some strong requirements like availability and response time. State machine replication is one such an approach to improve the availability and provide more reliable services, while still keep, from the point of view of both clients and application developer, a consistent and intuitive behavior. This means that even though we are adding more copies of our original server, clients and application developer can still see the system behaving like there was only a single server. State machine replication is an approach to improve availability, and it does so by increasing the number of copies of our original service. And if these copies, these replicas, start from the same initial state and execute deterministic commands in the same order, they will all evolve through the same steps, so the same state changes, and in this situation we can have some failures in some of these replicas, and the service will still be available. SMR, on the other hand, does not improve scalability. Since all the replicas need to exchange messages to define the final order of an operation, we have, in the best case, a situation where the performance or the latency will be as good as a single replica execution. In typical SMR protocols, a special replica called the leader is defined as the one to serialize all the requests. In the geographically distributed applications or services that I started talking about, we typically have some degree of locality, and this locality means that some objects are typically most accessed from some specific sites. These sites are called preferred sites for this specific object, and of course the preferred site may change over time. SMR cannot export this locality pattern. Even though the clients may be close to one of the replicas, these replicas still have to exchange messages to define the final order of the operation. So SMR does not couple with geographic distribution, at least the traditional approach. And we also introduce further questions. What if the objects are accessed consistent from multiple sites? We don't have a very clear locality here anymore. Can we even optimize for operation classes? Can we differentiate a write from a read operation? What if all these patterns change over time? Now we have locality, from sometime from now we don't have it anymore. So how do we couple off this dynamic of the system? These are the questions that we try to answer with GeoPaxos Plus, but before I present it, I'll just go through the system model. We consider a message passing, geographically distributed system, a synchronous system where process may only crash by failing. We have no Byzantine behavior here. Clients or server are located inside data centers, also known as availability zones, and these data centers are distributed over different geographic regions. An object may have preferred sites. These are the assumptions about the system model. GeoPaxos Plus is an evolution extension of GeoPaxos, which was presented in SRDS 2018. The main idea of GeoPaxos is to separate ordering from execution in an SMR protocol. So we also consider locality is tailored for locality. Object has a preferred site, and the replica in the preferred site of this object is the one that orders operation related to that object. Every replica still executes every operation, so we still have a fully replicated system. And we can have two kinds of requests, single and multiple serialized requests. I'll talk about that in the next slide. And all this dynamic is transparent to clients. In GeoPaxos, we can have a single serialized request, like the first one in this picture. In this picture, Replica 1 orders operations related to object X, and Replica 2 orders operation related to object Y. The first request is only related to X, so only Replica 1 defines the timestamp of the message, the request, before sending to all other replica for execution. The second operation is a request that accesses both X and Y. In this situation, we have a multi-serialized request where both replicas 1 and 2 have to exchange message to define the final timestamp of the message of the operation before it can be delivered to every replica and executed by every replica before going back to the client. In GeoPaxos Plus, we intend to optimize this object access, and we realized that the choice of serializer is key to performance, and it strongly depends on the latency among serializers. This influencing the multi-serialized operation, for instance. It depends on the workload. Do we have locality? Is this a uniform distribution? How do we deal with both situations? And we also consider different operation types, specifically read and write operations. In order to explain how GeoPaxos Plus works, I'll start with an example. Consider this example where we have three servers, A, B, and C. Server A, like in GeoPaxos, previous work, GeoPaxos, is responsible for ordering object X. Server B order commands related to object Y, and server C orders requests related to object Z. The latency, the round trip time between the servers are also written down here. Now let's consider a specific workload for object X only, where clients close to A execute 10 reads and 10 writes, clients close to B execute 100 reads and 1 write, and clients close to C execute 50 reads and 5 writes. Is this configuration the best choice if you only look at object X? It's obvious that it's not. In this example, most of the access come from clients close to B and C, so it's not a good idea to leave X being ordered by server A. We further extend this discussion and we realized why does it need to be ordered by a single replica? Why couldn't we put an object to be ordered by 2 replicas? And the consequence of this new choice is that now we have local reads. A read operation is always executed by the closest replica of a specific client. This increases parallelism and reduces latency. On the other hand, the price you have to pay is that a write operation is always a multi-serialized request. This means that we have to involve all the serializers for this specific object in order to define the final timestamp of a write operation. We also define an optimization model. To explain how it works, I'll go back to our example. Consider the same configuration, initial configuration, with the same initial workload for object X. In this situation, which is the best configuration? Where should X be? Who should order commands related to X? And which metrics should we consider to define the best configuration? In our case, we consider latency, and our optimization model considers all the possible configurations for placement of object X. So should X be ordered by server A, server B, server C, both A and B, A and C, B and C, or should it be ordered by every server in the system? Before you can answer this question, I'll present some assumptions about our model. The target here is to reduce the overall latency from the point of view of the client. And we have some assumptions here. The latency of a single replica request is always 0, no matter if it's a write or a read. This is the time to order a write or read request. Since the latency between servers is around 100 milliseconds, we assume that this latency to order the request inside a single replica is 0. The latency of multi-replica writes is 1 round trip to the farthest replica. I'll show in the picture how it works in the next slide. The latency of reads are always local to a single replica, so the latency of a read operation is 1 round trip to the closest replica. Or 0, of course, if the client and the replica are in the same network. The final cost of our optimization model is the sum of the latency for every single request. So if we go back to our previous workload example, we have here the calculation for every possible configuration, and the final optimum configuration is the one where X is ordered by both A, B, and C. In this configuration, the cost of a read operation is 0 for clients close to both A, B, and C, and the cost of a write operation is 10 plus 1 plus 5, 16 write operations, times the farthest latency here, 150 is the latency between A and B. So 16 times 150 is 2400. Having this calculation for every application object takes a lot of time. In our calculations, it takes 100 seconds for 8 groups and 1 million keys. So the idea here is to optimize this calculation. We do so by normalizing and caching the results. This means that a workload with 10 reads and 100 writes is equal to a workload with 1 read and 10 writes. The proportion is the same. The reason is the same. We also round up the results to reuse calculation from similar workloads, and we also use this hot replicas strategy. This means that if a replica is not accessed, clients close to a replica do not access very often an object, this replica is excluded from the calculation. By combining these 3 approaches, we managed to speed up the optimization process 50 times. So we went from 100 seconds to only 2 seconds for the same scenario with 8 groups and 1 million keys. We instantiated our protocol on a B+3 since it's a common and useful data structure. The only fields that you need to modify to cope with GeoPaxos Plus are the ones highlighted here. So we have a field for the list of serializers for this specific object, a flag to define if the object has been changed or not, and counters for read and write operations. The object here in our B+3 is a 3 node. We developed our prototype in C++. We have multi-threaded replicas with full copy of this B+3, and clients run in a closed loop with 1 client per thread. Our B+3 has a fanout of 100. This means that each 3 node can have up to 100 keys, and in the leaves of our B+3 we have 100 byte objects. We consider insert and get operations, and we also consider 3 access patterns. Locality, where clients in a site access the same subset of objects more often. Uniform, where clients randomly pick any object of the system. And skewed, where every client in the system accesses more often the same subset of the objects. We performed experiments in a local area network where we have more control and also in a wide area network where we can, as we can see, as a more realistic deployment. We evaluated our protocol against GeoPaxos itself, MultiPaxos, which we consider a baseline, and ePaxos, a protocol that can explore replica proximity to clients as well as ours. In a local area network, we have on the left the throughput analysis. So the maximum throughput, the darker bar is the one for GeoPaxos Plus. We can see that it outperforms the competitors in a locality workload with 3 and 5 replicas for mostly read operations. We have on the right the results that show that, unlike most SMR protocols, our protocol can scale as we increase the number of replicas. As we go from 3 to 9 replicas, the throughput grows linearly for the same deployment, locality workload, and 90 and 100% read operations. In a wide area network, specifically on Amazon EC2, we have similar results. The darker bar on the left shows that the throughput for GeoPaxos Plus is sometimes more than twice the throughput for the competitors. Here we have all the 3 workloads: locality, first locality, then skilled workload, and then uniform workload. In every situation, we have GeoPaxos Plus outperforming the competitors, and we have 90 and 95 and 100% read operations. On the right side, we also have results for the latency. The darker bar represents again GeoPaxos Plus, and we can see that we have the lower results for GeoPaxos Plus in every situation, with low, medium, and high contention in a locality workload. To conclude, I've presented GeoPaxos Plus that shows further improvement and extension to GeoPaxos. Now objects can have multiple serializers. We differentiate read from write operations. We presented an heuristic to define the best positioning, the best serializer for each object, and we also presented an optimization to this model. And the results show that GeoPaxos Plus outperforms MultiPaxos, GeoPaxos, and ePaxos by more than an order of magnitude in some configurations.